All right, good afternoon. Oh, I'm starting 10 seconds early. I'll wait 10 seconds. Yeah, how's everyone doing?
Pretty good. Yeah, I'm glad you went over that stuff in 224 because as soon as you did that and told us how to do the conditional statement for the string, everything worked.
Okay, awesome. Yeah, we'll use that trick a lot.
Yeah, I've never seen combining the two together, so that was kind of cool.
Yeah, there's other ways to do it, but that one kind of seems like the easiest to make sense of.
I didn't even know that function had an overload.
Which function?
Scan, SS.
Ah, yeah.
Scanf, sorry.
Yeah, scanf is awesome. All right, send me an attendance ping, please. Let me know you're here. All 14 of you. And any questions? I'll grade your homework and give you feedback on that in Canvas probably today or tomorrow. Remember, there's no classes on Friday, so we won't meet again until Monday. But I'll get you feedback before then.
Actually, I was going to ask you about that. Are we still meeting in 224 on Friday?
No, there's no classes at Clark on Friday.
Oh, okay.
Yeah, it's a student holiday, faculty work day.
I can't remember exactly what question it was, but it was towards the very end on the homework where we were asked to prove. Hang on a second. Let me see exactly which one it was. Yeah, 3.3 number 4. We were supposed to prove something that was equivalent to P or not Q. And I used the property of associativity where I made the preposition not Q or P.
Okay. Yeah, long as you end up with something equivalent, you should be good.
Okay.
Yeah.
I was going to use De Morgan's theorem, and then I realized, I can't use De Morgan's theorem in this kind of preposition.
Okay. Which question was this?
I got 3.3 number 4.
3.3 number.
Not Q as well.
3.3 number 4. You're writing a truth table.
Yeah, I did write a truth table.
Okay. Cool.
I thought we were supposed to do like an equivalent to P or not Q as well on the truth table, which is what I did.
Okay, cool.
Which is not Q or P.
Yeah.
Using associativity.
Okay. Yeah. Let's see. For the truth tables, were we supposed to write out the values for the individual components as well as for the smallest parts of the compound expression? So when you're asked to write a truth table for an expression, really what your final goal is, a truth table that shows all possible combinations of inputs and then has a column showing the output. But I recommend doing it in pieces where you write the truth values for the components of the larger proposition as well as the final answer column, only in terms of partial credit. If you're trying to write an equation for some expression and it's got 8 rows in it and 2 of those are wrong, well, you're probably not going to get a good mark on the problem. But if you did a lot of work to get to that answer and there was some small mistake you made along the way, and I can tell that from looking at the other columns, then you get lots of partial credit. So it's in your interest to show your work, and one way to do that is by just filling in those intermediate columns. But if a question asks for a truth table for X, you just have to show the truth table for X. Technically you're good. Yeah, so it's a partial credit thing. All right, so our plan today is to talk more about propositions and dig further into proofs. And I want to start off with some examples of propositions and using some of these things that we find from page 58 and 59, these basic logic laws and then implications and equivalences, using these to work from a starting point to a proof of something that we're asked to show. So I want to work through that in a number of different forms. I also want to talk about the difference between direct and indirect proofs and some of the things to watch out there. And then I want to take a look quickly at the homework that's posted for next Wednesday and see what we can say about that. Let me clear up a bit of confusion that I saw on Discord. So I tried to give you a cautionary warning about, prove, x is equal to y, right? Suppose we're just doing a mathematical proof. We want to prove that x is equal to y. And I said, here's something you don't want to do. You don't want to do something that changes this into, a square, and do something that changes this into a square and say this is equal to that, and therefore x equals y. Okay? That's not a valid proof. That's proving if x equals y, then, a square is equal to a square. But what you can do is, prove x equals y. Well, if I show that x is equal to x1, and x1 is equal to x2, and x2 is equal to x3, and x3 is equal to some square, and I can show that y is equal to, y5, and y5 is equal to q7, and q7 is equal to a square, I can use what I know about equality and say, x1, x is the same as x1, which equals x3, which equals a square, which equals q7, which equals y5, which equals y, and from there I can say, therefore, x equals y. That's a perfectly fine proof. The danger you get into is something like, prove x equals y. Well, x times 0 equals y times 0, 0 equals 0. Yes, I'm done. I've proven x equals y. That's not valid. Right? But this is not just, manipulating the left and right side. This is a series of chain rules basically saying, x is equal to this and that and that and that. And this is basically saying, that thing's equal to this, and that's equal to y. So there's, yeah.
It's proving it for a single value as opposed to all values in some set.
That's part of it, but it's something more than that actually. So this is just a fallacy, right? When you do this, what you're basically saying, is if this, then that. Right? That's what we do when we start off with a statement and we write other statements that follow from it. Right? And if this, then that, that's perfectly fine. But what people tend to do is they say, oh, since this is obviously true, this must be true. And really what you're doing there is you're saying, if this, then that. And that's not, that doesn't follow, right? So if 1 was equal to 2, then 0 would be equal to 0. That's a totally true statement. But I can't look at this fact that 0 equals 0 and say, oh, therefore 1 equals 2. Right? That's arguing in the opposite direction. But if I could do, something like 1 is equal to 2 divided by 2, which is equal to 4 minus 2 divided by 2, and I could do something like this and eventually show that that's equal to 2, then I've got a valid proof 1 equals 2. But I probably can't do that. And if that doesn't make a lot of sense right now, there's two possibilities. One, you already understand this to such a fundamental level that this just isn't registering. Or two, you don't understand this, and you'll end up doing this on a homework assignment, and I'll be able to point out specifics then, and at that point usually you'll figure out, oh, okay, I see what you're saying. So I'm trying to kind of like head off something down the road, but it may be inevitable. And if you end up doing this, you know, I'll point it out in the homework, and it'll make more sense then probably.
So you just, it's about modifying x and y and not about saying, well, if I'm going to assign x equal to 0 and y equal to 0, then 0 equals 0. Is that also the
Well, I didn't assign x and y to 0. I just multiplied both sides by 0. And if x equals y, then x times 0 should equal y times 0, right? Because we can multiply two sides. Well, I know x times 0 is 0, and I know y times 0 is 0. And I also know that 0 is equal to 0.
Okay.
But I think you'll see that this fact does not prove that fact, right? All I've proven is that if x equals y, then 0 will equal 0. But, you know, if x did not equal y, hey, 0 would still be equal to 0. So this does not tell me anything about the truthfulness of that. And like I say, it's probably pretty clear. I don't think anybody would try to claim that 1 equals 2 simply because 1 times 0 equals 2 times 0. But when these propositions are not so obviously false and are actually something you're trying to prove, this temptation comes in to try to just do things to both sides and then say, hey, I got an equality down here, so this must be true. So the easiest way to avoid this, keep in mind when we do a proof, we're starting with something that we claim is true, and then we write down true statements that follow from that. And all we ever prove is, you know, the next statement that we write. So if I start off and I claim that x equals y, I can do a bunch of things and I can eventually prove this statement. That's fine. But if I don't know if x is equal to y, I don't know if any of these other things are true. So we'll work through some proofs next, and we'll also work through the one case where we do sometimes start with something that we don't know is true. That's an indirect proof. And I think that will make more sense, but if not, keep asking. What's a good number of individual pieces of evidence to use when you're proving something? I don't think there's a well-defined answer for that. It's a good question, though. I mean, I guess ideally you'd like to use as little information as possible, maybe, if you're trying to make a proof that convinces others. But, you know, sometimes you need to use a lot of things to prove something. Some mathematical proofs are, you know, thousands of pages long. And are built on top of, you know, decades or centuries of previous results. One thing might be true for a certain scenario, but other factors would make something untrue. Yes, that's true. So we usually try to pin down the specifics surrounding. So, you know, if we try to prove something about, you know, some arithmetic expression, yeah, we probably want to be really clear. Is this an expression involving integers or real numbers or complex numbers or something like that? Is it best to focus on one side of the proof until it's equivalent to the other? Not necessarily. So a lot of the proofs that we'll work on and that you'll find in the book and that you'll see on tests tend to yield to the same kinds of approaches that we're going to use again and again in lecture and that you'll use on homeworks. But with kind of an arbitrary problem that you just bump into in the middle of the woods, right? You may have to do something to one side and then something to another side. You may have to do something, you know, that seems backwards. You may have to go down a bad path that doesn't take you anywhere but gives some insight and then come back and do something else and so on. So... All right, so let's try a sample theorem and a corresponding proof. And so a lot of these questions that we solve and the questions in the homework are already given to you in terms of propositional variables. And that's a little easier to work with, but sometimes we might be given a problem that is presented in words and sentences, and we need to change it into propositional language, and that's the homework problem you already did in your previous set. But let's play around with some sample equations. So here's a theorem that we're going to try to prove. So let me do P implies R, R implies T, not T. And our claim is that, sorry, not T. And our claim is that all of this implies not P. So when you see something written like this, first thing to remember is, you can throw in parentheses. This is claiming that these things imply that thing. Okay? It's not saying not T implies not P. Everything to the left of the double arrow taken together implies the thing to the right of the double arrow. And I've mentioned that in class last time, I mentioned it now, and it's also written on Canvas in the section that assigns homework 3. So don't get tripped up by that. A different way to write this would be as follows. If P then R, if R then T, not T, therefore not P. Okay, this is another statement of that theorem. So two different ways of writing the same theorem. And so we could say, our goal is to prove this. Another way to think about it is, if this, then that. Right? So this is like, kind of a super conditional statement to avoid, having to use parentheses. But if all of this stuff, then that thing. Okay, when you say if this, then that, it means assume this is true. Assume this is true. Assume these three things are true. And using the laws of logic, convince me that that is also true. That that is also true. And the laws of logic you get to use, that's this stuff. And it's this stuff.
What chapter is that under?
Chapter 3. All right, presentation matters. There's a few pieces to doing proof problems. If the problem is given to us in words, and word problems usually involve, politicians or dogs or, things like that. So if it's given to us in words, we need to translate it into something like this, the language of propositions. And then you need to figure out, why is this true given these things? And that's the super creative part. That's the puzzle solving part. And then once you figure that out, the third piece is you need to write up a proof. And if you don't write up the proof correctly, you get almost 0 points for the problem. Even though, the most important creative part, the part that's going to take the most work, the part that you're really after in this course, is figuring out, how do I prove this from those? You got to present it correctly also. So we're gonna go through this and we're going to think about it and figure out why this is true. And then we're going to write a formal proof for it. And you're going to want to do things very much the way that we're doing them here. So just kind of thinking about these three things. If these three things are true, is there anything else that we can say is true without having to do too much work, but maybe thinking about, some of these laws of logic? If we know these three things,
Can we say that P implies T?
Yeah, we can use a chain rule. Chain rules are nice because they take lots of things and they turn them into fewer things, right? If P then R, if R then T, well, that tells us, you know, if P then T. So I'm going to, you know, make a little scratch area. And I'm going to say ignore. And I'm just going to make a note to myself that, hey, I know I can prove if P then T. So now I got 4 things to play with. P implies R, R implies T, not T, and P implies T. So any of those that I can put together.
Well, I think I have a way we can prove it false, because using just how I forgot what the conditional's called, the arrow, but with that you can show that, when P is, the only time that it would be false, actually, wait, yeah, the only time that the conditional would be false would be when P is true. When P is false, T is true. Sorry, I mean,
Yeah, that's okay. I know what you mean. So it's false when P is true and T is false.
Also, we can't really see the scratch portion because of the window.
So I just wrote what you said. It's false when P is true and T is false. So what can we do from there? So look at these and look at what we know. We know this, 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 and this. Can any of these apply?
Since P implies T, if not T, then that implies not P.
Ah, which rule is that?
I don't know. That was just my own reasoning.
Okay, yeah, so that's called indirect reasoning. And it says if P implies Q and Q is false, then P is false. So we're using T instead of Q, but same thing. If P implies T and T is false, that guarantees that P is false. And hey, that's what we're trying to show. We're trying to show not P. So if we take this, and we take not P, and we use indirect reasoning, or sorry, we use not T, and we use indirect reasoning, we should be able to get to not P. So we've got an idea in mind, and you're doing this on scratch paper, or you're doing it in pencil or a whiteboard or something. We're just kind of kicking around the ideas and saying, okay, I think I see a path. I'm going to take P implies R, R implies T. I'll put those together to get P implies T. And then I'll use that with the fact that T is false, and I'll say indirect reasoning says, therefore, P is false, and that's what I'm after. So that's a clear enough idea now that I can actually write this proof out. Okay, so that was the second part, right? Which was coming up with kind of the intuition and figuring out why this is actually a true theorem. Now we're going to write it up. Okay, so here's how we can present this. So each statement that I write has to be a proposition. That's the first rule. Every statement of your proof must be a proposition. You can't just write X, right? You can't just write, X plus 2. It's got to be a proposition. So my first proposition, I need to say, P implies R and R implies T. I'm going to put those together. So my first statement is going to be the proposition P implies R. And everything I write had better be true, otherwise the proof is not valid. So why do I know that P implies R is true? It's a hypothesis. right? It may be true, it may not be true, but when we're looking at a theorem like this, we're saying if this, and this are all true, then that. So how do we prove what I just said? Assume this, and this are true, and then show logically that this is true. So we're going to assume P implies R, but our reason for it is that's a hypothesis. It really means we're just assuming, but that's why we're assuming it. All right, and I want to put that together with R implies T. So my second step of my proof is going to be if R, then T, and that's also a hypothesis. Now I want to chain rule those. I want to put them together to get P implies T. So my third statement is going to be if P, then T. And my reason, my justification for that is chain rule. And I'm going to list the two hypotheses that I chained together. And a guiding principle you can have in mind when you're writing up proofs is, you're going to present this to somebody who understands, propositional logic, but has not themselves worked out a proof of this theorem. Your proof is basically showing them why this theorem is true. And you can assume they understand what a chain rule is. They understand what a hypothesis is, right? But you're showing them the steps that they would follow logically to go from here to there. So I'm not just going to write this down and say, look at it. You can tell it's true, right? I'm going to actually tell them. I'm using the chain rule with these two hypotheses. And then somebody who understands, CSE215 should be able to say, oh yeah, P implies R, R implies T. Okay, yeah, that gives you P implies T. I see that. Right? So they nod their head and they go on to the fourth statement of your theorem. And I'm going to use this together with not T to get not P. Well, I have to state that not T is false. So that's going to be my fourth proposition, not T. And the justification for that is that's a hypothesis. And now, if P implies T and not T is true, those two directly give me not P. And the reason for that is indirect reasoning. Using propositions 3 and 4. Right, so that's using this law of logic right here. Well, something great has just happened now, right? Using only the hypotheses of this theorem or laws of logic that are printed in our book, and so we believe they're true, I just managed to state that not P is also true. And that's what we were trying to show. So our proof is done. And we indicate that by saying QED. Which means this is what we were asked to demonstrate. And that's the end of my proof. So questions about that? Yeah, go ahead.
Right?
Say again?
They should all look like this, right?
They should all look like this, yeah. Obviously, the specifics will change, but everything should be true. You'll usually write some hypotheses, you'll justify each thing, and the last thing you write should be the thing that you're trying to show, and then you write QED to sort of hammer home that point.
On a homework like this, would there be anything particular to circle, or is it just kind of the whole thing?
It's just kind of the whole thing, yeah.
So is there any point to circle anything, or?
No. The circling is more like, if you're asked how many students are taking night classes or math classes and art classes together, right? And the answer is 17, right? Then you put a circle around the 17. But for homeworks where you're trying to do a proof, really the whole thing is going to be your proof. The only thing is, if you're doing like scratch work or something, mark that off to the side, draw a line, label it clearly, you know, ignore this. And it's useful sometimes to have that there when I'm trying to follow your work, but the proof itself, you know, just sort of go line by line, and the QED kind of says, you know, that's the final answer right there. So usually when we want to say and, we're going to use a caret, right? Normally if we want to say P and Q, we're going to say P caret Q. The only time really that we're going to use commas is when we're writing a theorem like this, right? And it would be clearer if I wrote this with carets, but when we're doing this kind of statement of a theorem, you usually see it done with commas. Just to sort of visually break up, you know, this from that, and because, you know, there might be things in here that include carets, like P and Q implies R, and so the commas are a different character. But when we're writing things, you know, line by line, or we're doing this stuff, always use the caret for an and. So this is always the way I want you to present your proofs. But there are different ways we could prove this. We could also use an indirect proof with this. And I'm not ready to do an indirect proof yet, but we'll do that shortly. But as far as presentation, right, I want you to state the theorem you're trying to prove, and then I would usually say, you know, proof, and then go line by line, number each of your statements, make sure every statement is a proposition, and give a justification for each statement. And if you do all that, you're good. All right, good to go on? So let's do a wordy problem. So let me make a series of statements here. So here's a theorem. Okay, if you send me an email, then I'll finish my homework. So that's a statement that I'm making, which is presumably true. If you send me an email, then I'll finish my homework. Okay. If you don't send me an email, then I'll go to bed early. If I go to bed early, then I'll wake up happy. So these are all hypotheses. And so the theorem claims that, you know, assuming that these three things are true, I can say, therefore, if I don't do my homework, then I'll wake up happy. So that's an odd little theorem. Probably an unfortunate one for CSE215. But we want to prove this is true. We want to prove that, assuming these three hypotheses, these three propositions are true, let's prove that this proposition is true.
One thing that I didn't 100% understand when I was looking over how a conclusion being false proves that the hypothesis is false, is that you can have, like, in one of the questions for homework, it had, like, if a number that isn't divisible by 4, then it is even. But, like, the number can be divisible by 4 and not be,
it can be even but not divisible by 4.
Yeah, and so, like, doesn't that mean that there's occasions where the conclusion will be true and then the hypothesis will still be false?
So this will come in when we talk about indirect proofs.
Okay.
And what you're looking at is the contrapositive versus the converse. So if you want to show if P then Q, it's not sufficient to show if Q then P. Because if Q then P is not the same as if P then Q. But if we can prove the contrapositive of something, then we've also proven that something. But let me do one more direct proof example here, and then we'll look at an indirect proof, and I think that'll answer your question.
Okay. Oh yeah, because right here it's just like, you can still finish your homework without that email. It's not saying definitively you need that email to finish it. It's just saying if you do get that email, you'll finish it. But that's not what you're trying to...
Yes, it's possible that you're going to do your homework regardless. But even if you end up doing your homework, whether you get an email or not, right, that doesn't affect the truth of this statement. This statement is making a statement about what happens if you don't do your homework. So if you do your homework, this statement makes no claim on how you'll wake up.
Okay, it leaves like, it solves a certain number of outcomes, but leaves some of them kind of up in the air. So
Yeah.
not conclusive.
Right, so if P, then 1 equals 2. Right? So if P is false, right, it makes no claim on whether 1 equals 2. If Q, then 1 equals 1. Well, if Q is false, this makes no claim on whether 1 equals 1. Right? If Q is false, I can't say this is true or false. If P is false, I can't say whether this is true or false. All I can say is if P is true, this is true. If Q is true, this is true. So these conditional statements are not equivalences, right? It's different from saying, P is the same thing as the proposition 1 equals 2. This is a one-way implication. If this, then that. But that's all it says. All right, so to prove something like this, right, what we want to do is get it into a language that we can work with more easily without getting tripped up with words. So we want to change it into something like this. And so this is, your homework exercise of taking compound propositions and writing them more simply. Now this is a proposition. I could say, let, P1 be this proposition, P2 is this, P3 is that. Let's prove P4. But if I do that, there's nothing, about P1 and P2 that relates them to each other. But if I break this into smaller pieces, then I have a chance of relating these propositional statements to each other. And so I'm going to, do sort of the first thing I might think of, which is look at each of these as an if-then statement. And let's just write propositional variables for these pieces. And then write this theorem as, if that first proposition, then that second proposition. So let me do the following. Let E be the proposition. You send me an email. let H be the proposition. I'll finish my homework. Let B be the proposition. I go to bed early. And I should have used something else for homework so I could have H be happy. Let S for smile be the proposition. I'll wake up happy. So this first proposition that we're told is a hypothesis, we can assume this is true, is if you send me an email, I'll finish my homework. So that we can write more succinctly as if E, then H. And our second hypothesis is if you don't send me an email, which is not E, then I'll go to bed early. So that's B. And our third hypothesis is if I go to bed early, then I'll wake up happy. And what we claim follows from that is if I don't do my homework, then I'll wake up happy. And so this is a statement of this theorem. And in order to prove this theorem, we need to prove that given these three statements, this fourth statement follows.
What if we run into a fallacy here, and the theorem is incorrect?
Then you send me an email and say, yo, what are you trying to do here?
Okay, so we won't get a fallacy problem.
So I may give you a question which says, prove the following theorem or prove that it is a fallacy. Right? And then you'd like to either find a proof or reduce this to something that you can show is a fallacy. Or, there might be a question like which of the following are true and which are fallacies, and so on. But usually if you're given a problem which says prove the following theorem, unless somebody messes up, it should be true.
Right. For that first compound proposition, if E then H.
Mm-hmm.
If E is false and H is true, what does that total thing evaluate to?
If E is false and H is true, this is still a true proposition.
Okay. So
Right.
that means that E could be false and H would be true. But then that would still mean that you went to bed early, which means that you woke up happy. So H was true. Okay, but it's not exclusive. It's not saying that you have to by saying not H.
Right.
It's only proving that case. Okay.
Yeah. And if we ignore all of this and just kind of play around with it a little bit, right? What does doing my homework have to do with waking up happy? Well, if I do my homework, right? Maybe you sent me an email, maybe you didn't. But I'm also saying that if you don't send me an email, I'm going to go to bed early. And if I go to bed early, I'll wake up happy. So whether I do my homework or not, right? The fact is, if you send me an email, I'll wake up happy. But we also know that if you do send me an email, I'm going to do my homework. And these two statements...
There's nothing denoting that's exclusive, because essentially what it boils down to is you could have, at the very bottom proposition there, you could have S is true and not H is false, and that would evaluate to a true statement.
So if S is true and not H is false, yeah, that's totally fine.
Yeah.
Yep.
It just throws me off because there's nothing like indicating that it's like not an exclusive proposition.
Right. And this is the funny thing with conditional statements. Funny odd, not funny haha. right? These conditionals are almost always true. The only exception is hypothesis is true, conclusion is false. That's when this conditional fails to be true. Any other case, it's true, including the really odd one where they're both false. All right, so we've changed it to this. We have to prove this theorem now. So let me work it like this. All right, so a pretty safe bet is to just start listing your hypotheses as being propositions. But sometimes, you know, it's nice to do this in the order in which it occurs to you. And we already noticed one thing. If we took those second and third propositions, we can chain them together, right? Given this and that, we could say if not E, then S. So let me start with that. Let me start with if not E, then B. And that's a hypothesis. And if B, then S, and that's a hypothesis. And if we string those together, if not E, then S, and that's the chain rule, putting 1 and 2 together. All right, we're trying to get to if not H, then S. Any ideas?
My intuition is saying, well, if not E, or if E, then H, then there would be a, if not E, then not H.
Okay.
I don't think that's necessarily true.
But that's close. So we haven't used this proposition yet. Sometimes there's red herrings. Sometimes there'll be propositions you don't use. But usually you're going to end up using all the things that you're given as the hypotheses. So let's go ahead and just restate this hypothesis. If E, then H. And the inverse and converse are not equivalent, but the contrapositive is. And, you know, since we did some work here and we've got a not E implies S, we'd like to have something that implies not E. We could chain that together. And so doing these proofs is like puzzle solving. And it's kind of like physics problems this way. There's no algorithm we can follow reasonably that will tell us what to write down next. It's a trial and error thing. And you kind of go through, you know, this table of things that you have at your disposal. So you go through these, and you go through these, and you try different things. And you know, we've got 4 things written down, and we've kind of used all of these. And you know, how can we put these together? So somewhere in playing with this, you might randomly try this, or if you've done this a few times, you always know that we can change something like this into something like this using what we call the contrapositive. And so in this case, I'm taking the contrapositive of 4, and if this is true, its contrapositive is also true. But in my mind's eye, I saw that if I did this, I'd have a not E on the right here, and I have a not E on the left up here. And I'm thinking I can chain those. So now I'm going to say this implies not E implies S. I'm going to put those together and say the reason for that is the chain rule. And what did I chain together? I chained 5 together with 3. And guess what? We just proved the thing that we're trying to show. Not H implies S. And so we can say QED, and we're done. All right, questions about that? So let's talk about indirect reasoning. And there's two ways to think about indirect reasoning. There's kind of an intuitive way, and then there's the strict mathematical way. So let me tell you the intuitive way, and then we'll make it strict and mathematical like. Suppose you want to prove that if P is true, then Q is true. And P might be, a list of 5 propositions. We're going to assume 5 hypotheses. But generally, we're trying to prove if P is true, then Q is true. So what we've done so far are what are called direct proofs. And a direct proof says, okay, let's assume the hypothesis is true, and then let's do things that are logical and write down more propositions until, somehow magically we end up writing down the thing that we're trying to show, Q. And this proof, demonstrates that if P is true, then Q is true. And so we can say, which is what we were asked to demonstrate. Okay, an indirect proof works like this. We're trying to prove if P is true, then Q is true. Okay, I'm going to start off with not Q, and this is an assumption. I don't know if this is a valid statement or not, but I'm just assuming, suppose not Q is true. And I'm going to go ahead and I'm going to find things that follow from that. And suppose I come up with a conclusion that, 1 is equal to 5. Or I come up with some kind of absurd conclusion here. This is a valid way to prove that Q is true. And the logical way of thinking about this is, if Q is not true, I can show that 1 equals 5. And we know that's ridiculous. So Q has got to be true. Because if it's not, hey, 1 is equal to 5 and math is broken. So this is an example of an indirect proof, or sometimes called a proof by contradiction. And this can be any contradiction. It could be 1 equals 5. It could be the moon is flat. It could be that, tomorrow will occur before yesterday, right? But if starting with this, I can prove a contradiction, I can prove something that's not true, right? Then this thing has got to be true. Not Q must be false. But the most common contradiction that we'll end up with in an indirect proof, where we're trying to prove if P then Q, would be to prove not P. Because when we're trying to prove if P then Q, right, the idea is start off assuming P is true. But if P is true and not Q is false, if I can prove not P, well, I've proven P and not P. And that's a contradiction. So more generally, if you can come down and you can prove that false is true, that's a really strong contradiction. False cannot be true. So you assume not Q, and then you try to work logically from that and prove that false is also true. That's enough to say, hey, there's a problem. But if we think of this differently, if we start with not Q and we eventually come down to false, what have we done? If we think of this as a direct proof, we've shown that not Q implies false. Well, if we take the contrapositive of this, this says not false implies not Q. Well, not false is true, and not Q is Q. And so this proof is actually proving that if true is true, then Q is true. And we know that true is always true, so this is equivalent to Q. So this is really just a proof of Q. So you have a choice how you want to think about this. You can think of it very rigorously as we are proving, you know, the contrapositive. Or you can think of it as, let's make an assumption and argue to a contradiction, and then we can say that assumption must have been wrong. But this is what's actually underpinning it.
So essentially, when you're doing the truth table, that was going true, true, false, true. You're instead of searching for the to prove the three truths, you're searching to prove the one false.
Maybe. I gotta think about that. That might be a way to think about it. What we're really trying to do is.
You're saying the opposite of those three truths are
Yeah, but the truth value of this is exactly the same.
Okay.
Right? Because this and that are equivalent to each other. That's something that we call the contrapositive.
Okay, yeah. Yeah, it's kind of like you're just flipping the.
Yeah, if this flips around in your head a bunch of times, that's a good sign. Because it is kind of flippy.
Yeah, it's just really trying to get that that one false like justification is throwing me off.
Yeah, yeah. The funny thing is, the more you do this, if you do this enough, eventually it will click. But then once it clicks, if you try to explain it to somebody else, it's really hard. Because it's almost like it makes sense at some deeper level, some level deeper than verbal explanation.
It's just because you're proving rigidly that these are exactly true, and there are cases where that third one could go either way. It's kind of like when you have X's on the Karna maps.
Mm-hmm.
And like you're not sure what the outcome is, so you just like you can't conclusively prove it.
Right, right.
Yeah, so I'll let that topic rest.
Okay. There's plenty of reason and opportunity to readdress it as we go. So let's do an indirect proof of this earlier theorem. So we were trying to prove P implies R implies T, not T, and therefore not P. So let's look at an indirect proof of this. So let me just start off by stating the hypotheses. So I've just written down 3 hypotheses. But let's suppose that P is true. And I'm going to say negation of conclusion. This is really an assumption. We don't know that P is true. But I'm just going to, for a few minutes, assume that P is true. And I'm going to show you that something really weird happens. All right, so assume or suppose that P is true. And now the proof kind of develops itself, right? If P is true and P implies R, then we know that R is true, because that's the chain rule of 1 and, sorry, that's detachment or direct reasoning. Of 1 and 4. So detachment says if P implies Q and P is true, then Q is true. So if P implies R and P is true, then R is true. So that's detachment. And I can do that again. R implies T and R is true. That means T is true. And that's detachment. Using propositions 2 and 5. Well, every one of these statements is true, right? Which means that, since statement 3 is true and statement 6 is true, then not T and T is true. And that's just, using statements 3 and 6. And I know that not T and T is false. Right? Anything ANDed with its negation is always going to be false. That's the negation law. So P and not P is equivalent to 0, which means false. So that's the negation law. I've just proven false is true. Okay, that's a contradiction. So I do this for contradictions. It means something is wrong here. Well, I know these three things are true because those are hypotheses. This is the only thing I assumed, and by assuming that, I reached a contradiction. So this assumption must be wrong, and so I can say, therefore, not P. Right, and that's just coming from, if I assume P, I get a contradiction, so not P must be true. And that's what we were actually asked to show. That's the thing we were trying to conclude in our theorem. So that's an indirect proof. And usually, one of these directions is easier than the others. Sometimes it's almost impossible to do a direct proof, and an indirect proof is very easy. And sometimes the other way around. All right, questions about this? So let you think about this for a few minutes and stretch our legs and come back in 2.5 minutes, ask me questions about this. All right, so questions. So a lot of this, you don't really know what your questions are until you start doing some of these. And there's a ton of homework questions on this. So there's good opportunity to practice this. So quick look at the homework. So 3.4 number 2, 3.5, 2, 4, and 6. All right, 3.4 number 2. Show that the common fallacy is not a law of logic. We're going to talk about fallacies in a minute in general. But how do you show that something is not a law of logic? Well, you could find an example where this is not true, or you could use a truth table, right? There's different ways to do it. But this statement is saying, again, all of this stuff to the left of the double arrow, if all of that is true, then that is true. And you want to show that this is not a law of logic. So if you can find specific propositions P and Q where you can clearly illustrate that these things do not imply that thing, that's a valid way to show this. But they've got to be clear propositions, probably propositions about, you know, something involving arithmetic or numbers or something maybe would work there. Or you could try to use a truth table or something like that. So that's one to play with. And then 3.5 gets you into writing proofs. So question 2, prove these with truth tables. Right, and so these are propositions involving, you know, a small number of variables. Truth tables are fine. But then question 4, you want to use direct and indirect proofs to prove these 3 things. So you're going to do a total of 6 proofs for question 4. You're going to do a direct and indirect proof of A, and then a direct and indirect proof of B, and then a direct and indirect proof of C. So 6 proofs total. And then question 6 is a word problem. So question 6 says, determine the validity of the following statement. For students to do well in discrete math course, it's necessary they study hard. Students who do well in courses do not skip classes, and students who study hard do well in courses. Therefore, students who do well in a discrete math course do not skip class.
So for that one, we're kind of doing what we did before, where we'll basically assign a variable to the statement and then prove it.
Mm-hmm. Yeah. So translate it into, you know, a form where you have propositions and rewrite those statements in something like this and come up with a theorem that you're trying to prove. And then either prove it or explain why it's not true. All right. Let me make a comment. Let me say, don't do this. So this was our direct proof of that theorem, right? Trying to show that these 3 things imply that. So we stated 2 hypotheses. We chained them to show P implies T. We said not T is a hypothesis. We used indirect reasoning and we got not P. That's a direct proof. It's a direct proof because we started with the things that we are assuming are true, the hypotheses, and we worked logically until we proved the conclusion. An indirect proof we would do by starting off with, you know, hypotheses and the negation of the conclusion and then arguing to a contradiction. But here's what students sometimes do, and this is technically an indirect proof, but it really kind of misses the idea, right? So let me label this, don't do this. And this is not terrible. This is a valid proof, but it's really not an indirect proof, at least not in the way that I'm asking you to do an indirect proof. So you could say, P implies R, and R implies T, and P implies T, and not T. And I'm going to negate the conclusion, so I'm going to assume P is true. And then I'm going to put these things together and get not P, and hey, there's a contradiction. And technically that's an indirect proof, but really what you did was you did a direct proof of this, right? And then you threw some indirect language on top of it, which is, let's suppose that P is true. Well, this is a contradiction, so P must be false. So when you're trying to do an indirect proof, start off with, the negation of what you're trying to show, and try to use that to argue to a contradiction. Rather than, starting off with a negation of what you're trying to show, and then doing a direct proof to show that, the thing you're trying to show is true.
Are we gonna do I guess maybe compound proofs at some point, where we have to prove if we're proving and, we could prove those two variables separate.
So if you had a bunch of stuff and you were asked to prove P and Q at the end, it's really no different. Now you could do this by proving P and then do this by proving Q and then show P and Q, but there may be a way to, actually derive this from what you're told is your hypotheses. But it's the same idea. Because, even though we're using a single letter here, not P, or a single letter somewhere else, Q, right? That's just a proposition. It could contain disjunctions, conjunctions, conditional statements, biconditional statements, existential quantifiers, any of that stuff, right? And that's sort of the beauty of propositional logic, is that, if we can prove that these things imply that, it doesn't matter what these propositions are. This could be the proposition that, A and B and not C implies D or not F. And as long as, these hypotheses are true, I know that conclusion is also true. But yeah, if you see something like, prove this thing, it's exactly the same procedure. Let's see, indirect proofs basically want me to make the end result the opposite the proposition intends, and the contradiction indirectly proves the proposition. Yep, you got it. All right, let's talk about fallacies. And one of those homework questions mentions a fallacy. So we know about laws of logic. We know about, detachment and indirect reasoning and disjunctive simplification and all these fancy sounding things that we have, in these tables. But there are some statements in logic that we can make that are absolutely not laws of logic, right? Things that we call fallacies. And so let me show you the two common fallacies we work with in here. So if P implies Q, and if not P, then not Q. This is a fallacy. And it's called the fallacy of denying the hypothesis. The claim of this false theorem is if P implies Q, and if P is false, then Q is false. And that is not a law of logic. It's a fallacy. Now, it's possible that P implies Q and P is false. It could be that Q is also false. But it could be that Q is true. We cannot assert whether Q is true or false simply by knowing these two things. All right, have a good one. All right, so example, let P be the proposition I won the lottery. Let Q be the proposition 1 plus 1 equals 2. Well, I think you'll agree that if I won the lottery, 1 plus 1 equals 2. Right? If I win the lottery, I'm not going to change the law and suddenly make 1 plus 1 equal to 3 or something, right? So this is certainly a true statement, right? It's true because Q is always true. I switched to uppercase Q here, right? So this is always true. And it turns out I did not win the lottery. But can we conclude, therefore, that 1 plus 1 is not equal to 2? That's not logical reasoning. Okay, so that's an example that shows that this is a fallacy. This is, at least in some cases, not true. So that's the fallacy of denying the hypothesis. It's a fallacy you get when you assume the hypothesis is false, and then you argue to some non-logical conclusion. The other fallacy we'll see is P implies Q. Q, therefore P. Okay, and this is the fallacy of affirming the conclusion. So we can use these same propositions to see where this is a fallacy. If I win the lottery, then 1 plus 1 equals 2. Well, that is definitely true. 1 plus 1 does equal 2. That's also true. Therefore, I won the lottery. Well, that doesn't follow logically from those. It's not that easy. Correlation is definitely not the same as causation. That's actually a bigger issue in all of this. But yeah, so if P then Q doesn't mean that if Q happens, then P must have happened. And that's what affirming the conclusion is trying to claim.
Yeah, that's what I meant for just those two fallacies.
Yeah, that's good. That's a good way to think about it. All right, got a few minutes left. Let me leave you with a fun thing to think about, which is the square root of 2. So this is what I mentioned in the beginning of the course about the Greeks and the idea that if you make a square with sides of length 1, you have a diagonal. And they wanted to know what was the ratio of whole numbers that gave you the exact length of that diagonal. In other words, try to express the square root of 2 as a ratio of 2 integers. And I'll show you what happened when people tried to do this. So, send me an attendance ping right now, because if I run a few minutes late, I don't want people to have to stick around. But send me a parting attendance ping. But let's do the following. Let's assume square root of 2 equals a over b, where a and b are integers. And I'm going to make one more assumption. A and b have no common factors. In other words, a over b is in simplest form. So I'm going to assume that the square root of 2 is expressible as a fraction of two integers. And I'm going to assume that, if both of these are multiples of 3, I'll divide the 3 out. Or if they're both multiples of 2, I'll divide the 2 out, so that this is in simplest form, right? There's no way to make a simpler fraction. All right? So we're going to assume this, and we're going to argue to a contradiction. And once we reach a contradiction, that's going to force us to admit that square root of 2 can never be written as a fraction of two integers. And that'll prove that this is an irrational number. And it only takes a few steps to do this. So let's suppose square root of 2 is equal to a over b. All right, I'm going to square both sides and say 2 is equal to a squared over b squared. And that's a valid thing to do, right? I can take this side and square it and that side and square it. If these are equal, then these are going to be equal. And that tells me that 2 times b squared is the same as a squared. And that tells me that a squared is an even number. Because, b is an integer, b squared is an integer. 2 times anything is even, so a squared is going to be an even number. Okay, so here's a fact we'll prove next week. If the square of a number is even, that number also has to be even. So for example, if I take an odd number and I square it, I always get an odd number. And we're going to prove that next week. That'll be a pretty straightforward direct proof. So if you square an odd number, you get something odd. So if the square of something is even, we'll be able to show that that number itself, a, is even.
I don't think 5 squared is 5.
How about that?
Yeah, that's a false statement.
Okay, we didn't break math then. Yeah, 25. Thank you. All right, so we know that a is an even number. So whatever ratio the square root of 2 is, the number on top has to be even. All right, well now I'm going to take this and I'm going to move the b squared over to the left. And I'm going to say 2b squared equals a squared. Okay. And since a is an even number, I can write a as 2 times some integer. Even numbers are divisible by 2. So a is 2 times some integer c. And so a squared is equal to 2 times c squared, which is 4c squared. And if I divide both sides by 2, this will tell me b squared is equal to 2 times c squared. And 2 times anything is even. And so b squared is even. And so as we said up here, if b squared is even, b is even. And so if you can write square root of 2 as a fraction of two integers, both of those integers are divisible by 2. And that violates our assumption that a and b was written in simplest forms. And that contradiction forces us to conclude that the square root of 2 can never be written as a ratio of two integers. And that's a one-page proof that the square root of 2 is irrational. And there's no funny business in there. We'll do proofs later where we have some funny business and the proofs are actually like not valid for sneaky reasons. But this is a perfectly valid proof. And this was discovered thousands of years ago, and it proves something that is not at all obvious. That, this quantity whose square is equal to 2 can never be a fraction of two integers. I don't think that's an obvious fact to anybody, but it turns out to be true. And this is a proof of it. All right, well, I did that with 11 seconds left in class, so that was good timing. again, no classes on Friday. I won't have office hours on Friday, but I will have office hours on Thursday and on Monday. So work on the homework. Come by tomorrow if you've got questions on it, or come by Monday, or I'll just see you in class. All right, have a good one. Take care. Talk to you later.
What is the last thing that says B is the circle B is
Even.
even?
Yeah.
Oh, B squared is even.
Yeah, B squared is even, therefore B is even.
I have a question about proofs.
Okay.
You said there's a direct proof and then there's an indirect proof.
Mm-hmm.
I mean, if you use it in a direct proof, that proves that statement is true, correct?
Mm-hmm.
And does the indirect proof kind of prove that it's not true? Is that what it is? Or
Well, if you want to prove that P implies Q. So a direct proof, we start off with P, we argue logically, and we end up with Q. An indirect proof, we start off with P, and we assume not Q, and we argue till we come up with a contradiction.
okay, so you're trying an assumption that we call it the
Conclusion?
conclusion is false.
Right. And we argue to an absurdity, and then we say, okay, so I guess the conclusion must be true.
Okay, thanks.
Yep, you got it.
You're arguing that the Q being false is impossible. So
Yes.
It must be true.
Exactly.
Alright, thank you.
All right, you're welcome.
Thank you.
Yep, have a good one.